Okay, so today's notes are on solving systems with graphs. Our content objective is to solve systems of linear equations using graphs, and our language objective is to define terms including systems of equations, consistent systems, including dependent and independent consistent systems, as well as inconsistent systems. Um, so let's jump right in. I started by defining some of those terms I just mentioned. So first one, a system of equations. We talked about this briefly in our last video. But a system of equations is a set of two or more equations. So last lesson we learned about systems of inequalities, which was the same idea as a set of two or more inequalities. Now we're talking about equations, but it's the same general idea. A linear system is a set of two or more linear equations. So you can have systems of equations where it combines quadratics and linear, or absolute value and linear, or absolute value and quadratic. But a linear system is specifically a set of two or more linear equations, which is going to be our focus for this unit since it's on linear systems. A solution of a system, which is what most of our lessons this unit are going to focus on, is a set of values for the variables that make all of the equations true. So it's a set of values for the variables. If you can't read that, that's a B, that make all the equations true. So it's the points, which is the points where the lines intersect. So usually this is going to be one, for linear systems, this will be one coordinate point. If we mix a linear equation with other equations, we could get more possible solutions. Our inequalities was that whole shaded section of our coordinate plane. But for today and the next couple lessons, we're going to be focusing on finding the solution of a system, which will be one coordinate point, or one x and one y value. So again, this is a whole unit because we can solve systems with several different methods. So we can solve with graphing, which is what we're going to focus on today. We can solve systems of inequalities with graphing as well, which is what we did last lesson. And then next lesson and the following lesson, we're going to focus on substitution and elimination as methods for solving a system. And then another way you can solve is with matrices, though we're not covering this in this course. There's some easy ways to do that on a graphing calculator as well. Or you can do matrices by hand, but we're not going to focus on that this year since these methods are usually plenty sufficient to solve any system we will encounter in this class. So I'm going to flip the page so I have plenty of room for my first example, which asks, what is the solution of this system? And I have negative 3x plus 2y equals 8 and x plus 2y equals negative 8. So I'm going to start this. So my goal is to solve the system or find this point of intersection by graphing these two lines. So I think you guys can probably do that without an example, but just to make sure we're all on the same page, the way I'm going to solve this by graphing is by putting this in slope-intercept form. I could find the x and y intercepts and plot those and graph them, but for the sake of since I want to be very precise about which point of intersection I have, I'm going to put them both in slope-intercept form. This way I can, especially since I'm not using graph paper, this will allow me to be a little more precise. So I have negative 3x plus 2y equals 8. And I'm going to add 3x to both sides first. So I have 2y equals 3x plus 8. Then I'm going to divide everything by 2, and I get y equals 3 over 2x plus 4. So again, I just added 3x, divided everything by 2, and here's my first equation. My other one, I have x plus 2y equals negative 8. I'm going to subtract x from both sides. I get 2y equals negative x minus 8. Divide everything by 2, and I get y equals negative 1 over 2x minus 4. So here is my second equation in slope-intercept form. Now I'm going to graph both lines. And I'm going to make note this needs to be precise. So I'm going to say precisely. Precisely. This is important because we're going to use our graph to find our solution. So if we're not graphing this accurately, then we're going to end up with a graph that does not give us the correct solution. So it's going to be really important that I graph this correctly. I have x and y. I'm going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. All right, so if I graph my first line, I'm going to start at positive 4. So I go up to 4, put a dot, and it's a positive slope of 3 over 2, so I go up 3 over 2. So if I imagine this one would be about up here, I can go down 1, 2, 3 over 2 the other way, down 1, 2, 3 over 1, 2 the other way, and down 1, 2, 3 over 2 the other way. I'm not worried about my dotted and dashed lines because these are all equations, so they're all equals to, they're all solid lines. So there's that one, and then I'm going to graph the other one starting at -4, so down here, and this one has a slope of -2, so I'm going to go up 1 over 2 this way, up 1 over 2 this way, so I already found their point of intersection, up 1 over 2 this way, just to make sure I keep graphing. And then I'm going to connect the dots. So I've graphed this line. Here is our point of intersection. So I graph the lines, I identify the point of intersection, and that is my answer. So this is at 1, 2, 3, 4, -4, and then 1, 2, -2. So my solution is -4, -2. If I wanted to be sure that I properly identified this point, you can always check your solution by substituting into both original equations. So just to make sure we did this correctly, since we're not using graph paper, I'm going to practice that. So I have -3 times -4 plus 2 times -2 equals 8. So we'll see if this works. -3 times -4 is positive 12. 2 times -2 is -4. 12 minus 4 is 8. So that one indeed works. If I try it on the other one, I have -4 plus 2 times -2 equals -8. -4 minus 4, and that is indeed -8. So that one works out. So the solution of the system is -4, -2. So that is our answer for this problem, and that's all we have to do for that example. All right, there's a couple more definitions I want to talk about with you guys that I mentioned in the language objective, so I'm going to flip the page to talk about some of those. So one thing I wanted to talk about is consistent versus inconsistent systems. So consistent, sorry, I'm writing this wrong. Consistent, that's an I, sorry, consistent systems are systems that have or has a or multiple solutions. So consistent systems has a or multiple solutions. So they can be, there's two possibilities. If a system has a solution, it is consistent. So as long as there is a solution, it is consistent. But it can either be dependent, and this has infinite solutions. So dependent systems have infinite solutions. So what this means is they're the same line. So if you have a consistent or a consistent dependent system, what that means is that you have a system that is just the same line. It's two of the exact same line on top of one another. So there are infinite solutions. Like every single x and y makes both equations true. So that would be a dependent system. You could also have independent systems if there is a solution. So if it is consistent, it can be dependent, which is this, and have infinite solutions, which is the same line, or it can be independent, which has one or limited solutions. So it can, when we're talking about linear systems, it would only have one. So consistent independent systems have one or limited solutions, whereas consistent dependent are just the same line, they have infinite solutions. And this is compared to inconsistent systems, which have no solutions. They are just parallel lines. So inconsistent systems are parallel lines because there's no place that they will ever intersect. There's no place that there's no point that will make both equations true. So if we have independent, they're just intersecting at one point, coinciding is the same. So I'll draw a few more examples. Actually, I'll skip that for now because this is just the main takeaway that I want you guys to have. Dependent is the same line, infinite solutions, independent, one or limited solutions. Both of those types are consistent because they have solutions. Inconsistent have no solutions, they're simply just parallel. The last thing I want us to do is classify. So I'm going to try to have you guys do this as a quick check. Determine if the following systems are independent, dependent, or inconsistent. So all this requires that you do is figure out if they're parallel, or if not, if they're the same, if they're the same or if they're not the same. So the first one I'm going to have us try is negative 3x plus y equals 4 and x minus 1/3 y equals 1. So for this one, I'm going to start by putting them in, or I'll write both of them. The other one I want us to do is 2x plus 3y equals 1 and 4x plus y equals negative 3. So the way I'm going to do this is put them both into slope-intercept forms, so that's easier to see if they're parallel or not. So if I rearrange these into slope-intercept form, I get negative 3x plus y equals 4. I add 3x to both sides, and I get 3, or y equals 3x plus 4. If I do the same thing with the other one, I get negative 1, or x minus 1/3 y equals 1. I subtract x from both sides, I get negative 1/3 y equals negative x plus 1. I multiply by negative 3 to cancel that, so I'll write this step out since I know a lot of people will forget that. I multiply everything by, negative 3. I'll write that in front. Negative 3, and I get y equals 3x minus 3. So here, I see that these actually have the same slope in different y-intercepts. So m1 equals m2, but b1 does not equal b2, so these lines are parallel. So these lines are going to be inconsistent. So all I did here was rearrange them into slope-intercept form, realize they're parallel, and label them as inconsistent. I'm going to do the same thing here. So if I rearrange this one, it becomes y equals negative 2/3 x plus 1/3. And then this one will become y equals negative 4x minus 3. They don't have the same slope, they don't have the same y-intercept, and they're not the same line. So it's going to be independent or consistent independent. Since they have different slopes, different y-intercepts, they're going to be consistent dependent because they are not parallel and they are not the same line. So that's all for today. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.